Good evening, Dr. Balogun.
Good evening, Dr. Zalapo.
Yeah, good evening. Yeah. Yes, that's great. So, Dr. Iroa, you people, you refuse to follow our discussion on Tuesday? You and your husband?
So I've actually been on call. I've been on call throughout the week. So
even on call, you can use your phone if it's not computer. Because that's what some people do. For some folk do. They use their phone. Yes, I mean now. Because that one say, I will not even ask you to even run any, because that one we are not running anything. It's just to talk into the air. And it's a large crowd, people just come. So yeah, sometimes there are some things that I've said, though you will keep on hearing, though, because there's an assumption, some assumption that, because your understanding of this is when you hear, it's more like faith come by hearing. So it's the same thing. So let's quickly look at, we want to start with understanding t-test and the background information about t-test, so that we can move forward, because all we want to be looking at is how to compare means. And you either compare means, two means. Is how to compare two means. Because comparing, if you look at chi-square, when we discussed chi-square the other last week or 2 weeks ago, we have been discussing, more than even 2 weeks ago. So we have been discussing comparison of proportion. And that is, you can have two proportions. That is, you have summarized in percentage, which is proportion, for 2 groups or 3 groups, can be for many groups. So comparing proportion between groups, it can be 2 groups, can be more than 2 groups. But when it comes to mean, it's not the same thing you use to compare 2 groups, you use to compare more than 2 groups. And that is why mean is about comparing, yes, t-test is about comparing 2 means. So comparing more than 2 means, 3, 4, that one is ANOVA, it's analysis of variance. You don't compare directly because of family-wise error. It is when we discuss that, we talk about the reason we will not use mean. Not that you cannot do it, but it will lead to you comparing many mean at the same time. Sometimes if you are talking of 3 groups, you have to compare, you have to do 3 pairs. If you are talking of 4 groups, you have to do 6 pairs. If you are talking of 5 groups, you have to do 10. You know what it means when you are combining 6? That one you are close to 20. So it's cumbersome. So let's just, so here now we are talking of comparing 2 means. And if, because you know that we have 2 types of group of statistical tests, parametric and non-parametric. Parametric means that you follow an assumed distribution, normal distribution, and some other requirement like homogeneity of variance, that the variance of the group must be the same. Even if it's not exactly the same, it should not deviate much. So, and some other requirement like that. But there are some, if the data set cannot follow that distribution, you cannot use those parametric tests. So for the t-test now, for each type of t-test, there is or even sometimes more than one non-parametric counterpart. And this non-parametric counterpart are the one you now use instead. And we are going to be discussing how. Like on Thursday, I just gave the essence of do is for people, because many people, they don't know the usefulness. They don't even know that it's even easy once they understand the concept. That's why I discuss it, for people to know. But still, some people after they hear, they will not come for detailed training on it. But notwithstanding, let people know. So look at this to the t-test comparing me. You know that you can actually compare the mean with z-test, z. Because if something follow normal distribution, you can use that z-test to compare. So, but sometimes ago, you know that for something, even something that naturally follow normal distribution, like weight, like height, if the sample size is small, something less than 30, it will not be appropriate. It will not follow normal distribution. If normally it should follow normal, since the sample size is very small, it will not follow. And at the end of the day, you cannot use the Z distribution for it. So that was the origin of this t-test, t-distribution. The person that discovered it, this is the picture you are seeing. I think I've shared it. You are seeing my slide, right?
Yes.
Have we seen the slide?
Yeah.
Yes. So this is Gosset. Gosset was a chemist in Guinness, in Dublin. So he discovered that comparing, using Z-test to compare something of lower, I mean, when the sample size is very small, it's not appropriate. It's not appropriate. So that was how he, well, can we say he invented? I will not say he invented because all these things are there. To me, he discovered the T distribution. Well, you can say he invented it. It was the first to, though they said somebody described it before, but it was the first to describe it and publish it in 1908. And he used a pseudonym because by that time, because he was working for a commercial company, you cannot publish their data without permission. They will not even allow you because the commercial people, they will not allow you to publish their data because sometimes if it's not favorable to their image, so they will not want it. You cannot just for unless you want to dot the data set. Prof. Sorisha, your hand is making noise. You can mute yourself. Prof. Wakwe, you can mute yourself. You are making noise. Your computer is making noise. Okay, thank you, ma'am. So unless you dot the data, that is why they don't actually allow even publishing unless you get permission, and it may take time. So he was publishing. He now publish it under, instead of saying, it was a discovery anyway or invention. So normally we will have put Gosset test. They now put it student t-test. Student t-test. He was the one that called it student t-test. But the one he published was for independent. Now, as you know, whenever somebody discovers or invents something, some other intelligent people also will try to bring more out because there will be limitation of that thing. Maybe that thing cannot do for some other scenario. That was why one sample t-test came, peer sample t-test now came. But the first person to describe it is Gosset. Now that is the historical background. Now this T distribution. You remember when we discussed chi-square distribution, we trace the origin of chi-square to normal distribution because the first person also, Pearson, what he did was to square the standard normal deviate. So when you square all those negative signs left, you now get a distribution that is no more bilaterally symmetrical, but rather skewed to the right. So the same thing here. This person discovered that, look, the normal distribution will not go for situation where we have smaller sample size. That was how he invented this one. But this one also is bilaterally symmetrical. But the mean is not zero like that, only the thing is as close to normal distribution. Like any other probability density function, the meaning of probability density function is a graph that shows probability distribution. Since probability cannot be more than one, so the graph, the total area of the graph will be one. That's just it. Because all the possible probability of an event cannot be more greater than one. So because of that, even when you show it in graph, any form of probability distribution, either discrete, continuous, or whatever, like we know that normal distribution, chi-square distribution, T distribution, F distribution, they are continuous probability distribution. So because that, so even any probability, even either considered or not, the total area is one. So the total area under this one is one. Okay, I'll show you. But the first thing I want to simply, you can call it T distribution. When the sample consists of independent analytically distributed observation from normally distributed population, it's still for normally distributed population. So is a family. It's not like standard normal distribution, which is 1. So that one, they say the degree of freedom is infinity. That's standard normal distribution. But this one, the degree of freedom changes. Well, it's very simple. The degree of freedom is a function of, in many cases, not all cases. For when you are dealing with T now, when you are dealing with comparing means, it's a function of sample size, because is sample size minus 1. If there are 2 samples, each of them is sample size minus 1. But when you are considering categorical variable, the degree of freedom is the number of category minus 1. So when you cross tabulate, when you are looking at association between the 2 categories, so the 2 categorical variable, the degree of freedom would be number of row minus 1 times number of column minus 1. You know, each of them has their own category. So the degree of freedom for each group times the other one. That's just it. So you just know that the degree of freedom has to do with an entity minus 1. So that shows that for this case now, when it's not categorical variable, because the reason is that for continuous variable or for quantitative variable is not categorical, you cannot have categories. So you have, most of the time you may have limited number of possible value. So that is why each entity stands on its own. And that is why the degree of freedom is the total entity, that is sample size minus 1. But for categorical variable, you don't use that, because those ones, they are limited categories. So there are, when we say ethnicity, Hausa, all the words that are Hausa, they are 1. Even though if the sample size is 400, all the people that are Hausa, they are under 1 category. Yoruba 1 category, all that. So if you have limited category, the degree of freedom is number of the category minus 1. So when you are now looking at the association between 2 of the variable, so the degree of freedom will be the degree of freedom for this one multiplied by this one, because this one will have its own category, maybe it's 4, this one 3 category. It will be 4 minus 1 times 3 minus 1. That is for contingency table. So that is your, so the 14th distribution and the degree of freedom actually depend on the sample size. Is the sample size minus 1. If there are 2 groups, so each of them, the degree of freedom for the test will be n minus 1 plus n minus 1. So you can say n plus n minus 2. So it's a family distribution, because it's not only one type. It depends on the degree of freedom. As the number of degree of freedom increases, that distribution approaches normal distribution. That is one thing. So the mean will be 0 and the variance or standard deviation will be 1. So you are used for estimating mean of normally distributed population. So we use it for normally distributed population. Sample size, where sample size is very small, when standard deviation is unknown. You will see something very interesting. You will see that over the years, the T distribution has taken over. Is more popular than Z distribution in comparing means. Z distribution is still the most popular distribution. Normal distribution is still the most popular distribution in statistics and research, because it is the basis for hypothesis testing. Then when you come to comparing mean, T distribution is more popular than the normal distribution in comparing mean. So I've already said it, the probability density function is 1, the area under the graph. So the mean is 0. The distribution is symmetrical about the mean. The variance is equal to J over this. It's just talking of, because when you are dealing with 2 groups now, you're going to remove, you have to remove 1 from each one. The variance is always greater than 1, but approaches 1 when DF become bigger. That is, when the sample size increases, it will now be close to the characteristic of normal distribution. And let's look at it in a pictorial form. So this graph, they are just comparing normal distribution and T distribution, so that we can know how they differ and the relationship between them. The red is standard normal distribution, that is the Z distribution. The blue is the still distribution. You will see something because the area under is one. It's the same area under both of them. So if they are going to be different, the only main thing that can make them to be different is their height and flatness. So T distribution will go down, flatter and more spread. As the normal, it's very, in fact, if you remember when we discussed differential statistics that time, we talk about standard error. We say standard error when the standard, how do you get standard error? Standard deviation over square root of sample size. Standard error actually is the standard deviation of sampling distribution. I will not be repeating myself because we talk extensively. I don't know if anybody, I want to pause it because I will not, I want people to benefit also. I don't know if anybody have issue with understanding standard error. Do you have issue in understanding standard error? Because it's a key to understanding all these things. Because where is under introduction to inferential study, that's where I trash out standard error. Who has issue? Should I go over it? Standard error. Because you will see something here. Because it's a limited class, I have to adapt to your taste. It's not a large class and it's not, and this is a special class. I don't know if anybody has issue. Should I continue? Standard error. You will see when the sample size is very large, because standard error is a standard deviation over sample size. When you increase the sample size, the standard error will become smaller. When you decrease the sample size, the standard error will become bigger. And we say standard error does two things. It should indicate two things. If the standard error indicate how spread the attribute, how different the attribute in the population. Like for example, if you compare height and weight differ more in population than height. People have closer, that is my height may not be different from your height, more, but weight differ more than height. So if standard error is large, it should mean that the attribute. Hello? Sorry for that. Hello? Yes, my listening just log out. Okay. Yes, that's why the internet just went out. So that's why I quickly put my battery, my phone, to restore onto that one. And the thing is charging. I don't know why it just went off. Okay, can you hear me?
Yes.
Yeah, you can hear. So I will go back to that. So what I was saying is that when the standard error is very large, it may mean that the attribute is wide apart, the value is wide apart in the population. It may also mean that your estimate, what you estimate in your sample is too far from the parameter. What you can do what you estimate in your sample is statistics, like your mean, your standard deviation, your whatever you say you are calculating, mean, median, percentage, whatever you do in your sample is statistics, because the sample, if you have attended to all the elements in the population, you have not taken sample, you will get different value. So that is why inferential study, you want to know how close is that our sample statistic to the parameter. The real thing you are interested in is in the parameter in the population. So if your standard error is large, it may mean that your what you get as your statistic is too far away from the real parameter in the population. Can you see now? So two things, big standard error can. If the standard error is very small, it may mean that the attributes are very close, or your estimate is close to the parameter. But in this situation now, what we are looking at here is not. What we are looking at here is not whether your estimate is close to the population parameter. is attribute in the population. If your standard error is very small, the attribute, what that shows that the attribute, and if your sample size is very small, the value will be wide apart. The standard error will be very large. If you look at it, if standard error is standard deviation all over square root of sample size, it means that sample size is the denominator. If sample size is the denominator, so if you increase sample size, it will decrease the value. But if you reduce the sample size, it make it big. So that's what, if you look at it, they say that the t-test, t, when the is more appropriate for when sample size is very small. And as the sample size increases, it approaches normality, like a Z distribution, normal distribution. So can we see now, when the graph is wide apart, that is the way it's flat, it shows the variability is more, is indicating that, oh, this one, the sample size is very small. So as you are increasing the sample size, the degree of freedom is increasing, the standard error becoming smaller, the graph will be shrinking together. If the graph is it comes together, it shows that the standard error is very small. That's what it's showing here. So when the degree of freedom is very small, the t-test, what it does is that it is bilaterally symmetrical like this, but it's flatter and the base is wider. And that is what we are seeing here. The base is wider. Now, let's look at the second one. Sorry, I'm moving this, is covering my head. So let's look at the second one. You see, this third one, tall one, dark, is the standard normal distribution, and it's also t distribution when it approaches normality. When the standard error and when the sample size increases, you can see that the t distribution is like normal distribution. So the degree of freedom here is infinity, that is a large sample size. This the t distribution is like normal distribution. But when the sample size is lower, can you see? Is the peak of the graph is lower, but it's more widespread. The area under all of them is the same. It's like when you have something that is plastic, you can mold, you can flatten it, you can, the area is the same, but it's just the way the shape, either is flatter, you have a wider. If something is of the same length, if you mold it like this, it can be taller, but it will be narrower. If you expand it for it to be wider, the height will reduce exactly the same way, because the area is the same. Now, when you look at the third one, you will see something. I don't know if you can see that for normal distribution, the middle 95%, the standard normal deviation that correspond with the area. I think we discussed it. The area that is 95% is the standard normal deviation for the standard deviation, or number of standard deviation for normal distribution is 1.96. But for t distribution, what corresponds with 95% middle is 2.201. I don't know if you can see it, because it's wider. That is why it's like that. Now look at it. This one, still confirming the same thing. The blue one, this last graph, the Z distribution is peak. The red is
T.
When it's close to the normal distribution, when it's close to 30, when it's the degree of freedom, the sample size is close to 30. While the other one, the flatter is T, when the sample size is lower. I think you get the logic now. So all these three are seeing, the area is the same. It's the width and the height that differ. So as the sample size increases, this thing begin to shrink and begin to become tall and become like normal distribution. That's T. So you will see, what you will discover is that why T distribution now become more popular than normal distribution in comparing me. You will see the reason. You will see that generally Z tests are used when the last, we have just said it, last sample size. Then when the sample size is smaller, less than 30, T is more useful. But as both of them, they are doing the same thing. You will see this algorithm. Do you know, okay, you want to see which one should we use? The way to know the best to use per time, either Z or T to compare the mean, is, do you know the population standard deviation? Because for you to use Z, you must know the population standard deviation. You know, it's assumed that this thing follow normal distribution. So you must know the population standard deviation. If you know it, if you don't know it, just 1 minute. Yes, I'm back. If you don't know it, okay, there's still another question. If you don't know it, you use t-test, because you cannot do the Z without you knowing the population standard deviation. That shows that you have to in a previous study, you must be able to know what is the population standard deviation in the population for that attribute. But if you don't know it, you can use t. But if you know it, so if you want to, if the sample size is greater than 30, you use Z test. Otherwise, if it's less, you use T. You will now see 3 options. 2 are favorable to T. 1 is favorable to Z. So what is this one is showing is that what Z can do, T can do. So there is no need even using Z to compare me. The reason being that if the population is very small, the sample size, the sample is very small, you cannot use Z, you use T. Now, when even apart from the fact that you may not even know, even when the population is high, the sample size is high, apart from the fact that you need to know population standard deviation before you can use Z, the T also approaches Z. So the T become like Z, because as the sample size increases, it look like Z distribution. So that is why you know the cases you can use Z. You can use T rather. In all the cases, you can use T distribution. That is why T distribution become, so T test become more popular. Now, so I will have just put I didn't change this in computation rather than formula. I just want, before we go and run this, so let's just look at the logic. I don't want to bother us with, if for contingency table now, it's easy to put the value there, but when it comes to be dealing with many something, you will see we have example to run to do it. But look at, I discussed under assumption around hypothesis test. I said that all the tests, either chi-square, t-test, and over, is the same thing. It's the same logic. It's the same logic. It's the same cloth in different. It's the same thing in different cloths. Now, let's look at this. The statistic test. What you are actually looking at in statistic test is to look at the observed value, because you actually, in the test, you are trying to look at different between groups. This one, you're looking at different between 2 groups as per outcome variable. The outcome variable may be height, weight, between urban, rural, male and female, between 2 classes. So you are looking at the difference in their height, their blood sugar, their blood pressure. Is the difference you're looking at. So the observed value here means the value you got from your sample, and the difference also is observed value, is observed difference. Like for example, if we say blood sugar among women 65, blood sugar among men 60, you can see this 65, 60, the observed value. 5, when you remove 60 from 65, is observed different. You can see. So all this observed value is talking the value, all the different, they are all observed value. Then there is what we call hypothesized value. Hypothesized value means the value when no hypothesis is true. That is the value when there is no difference between them. What should be their value if there's no difference between these two groups? If you want to say, oh, the blood sugar between men and women, if there's no difference in the difference of blood sugar, you expect their mean when you to be the same. So when you now remove to be 66, you remove one to the, it should give you 0. So no hypothesis say there is no difference between the two groups. That's what non-hypothesis says. So hypothesized value means that what is the observed value of that difference when non-hypothesis is true that there's no difference between them. So observed difference will be 0. So look at that. Well, before we jump to that, so that difference, because that's what you are observing now. You are observing, okay, there's a difference, and I'm seeing this difference in my data. But the hypothesis says that there's no difference in the population. So what you're actually looking at, you now want to see, is there any difference in my observed and the population that there's no difference? The population that says there's no difference, the difference will be 0. And the difference you have gotten now. That's just it. So that difference, you still want to compare it if the difference, because there is inherent variability, which is standard error. If you look at the denominator, you remember I talked about standard error. Standard error in this sense that the usefulness of standard error here is that a characteristic that say, okay, if standard error is very large, it means that there is much variability in that attribute in the population. If the standard error is very small, there's less variability. So what you are testing that if you say you are observing different, the difference may not be significant if naturally that attribute vary a lot in the population. For example, now, the blood sugar about male and female we talk about. If the mean is 65 and 60, the difference of 5 is observed. But you will notice that even some women, you say that their blood sugar is 65. There are some women that got even less than 60, that their blood sugar is the average value you are telling us. Some of them may have even value less than some men. Even the men, you say that averagely their blood sugar is 60. Some men have higher blood sugar, even more than some women, more than the average for women. So sometimes, if the variability of that attribute in the population is large, you cannot say that little difference is a difference. So the logic behind the hypothesis test now is to now compare the difference you observe divided by the inherent variability. If actually the difference you observe, it means it's really different. When you divide it by the inherent variability, it should not be the same, because if it's the same, that shows that there's no difference. But if it's the same, it will give you 1. If you divide something of the same value, numerator is equal to denominator, it will give you 1. But if the difference you observe is far higher than inherent variability, which is the denominator, it will be greater than 1. If the difference is so much, it's not just greater than 1. It will be more reach a critical level. Not say no. The statistic will give a high value. That will not say no. The difference in this blood sugar, in this attribute, is much. Can you see the logic behind hypothesis? And the same thing, even the chi-square you see is the same. In all the something is different, same. So they now call it the systematic variance. The systematic variance is variance due what you are seeing, you are getting in your study. So though the word systematic, where they go, most of the people that are coined that word, they were people that were doing experimental research. They believe that the difference, if you do control, you perform experiment, you don't perform experiment on this one, you are subject and control. They believe that the difference is due to what they did. That's why they say systematic variance or systematic difference. But you are comparing with inherent difference, because sometimes there are some variation even without you doing anything, even without the research. So there's some variation among the thing varies among the population even without dividing them into groups, you are just telling us. That same male and female, and you are saying you are looking at, even among there are some very, so if the variability in the population generally is as high as what you have observed, it's not a difference. I think it's very clear. Like I want to stop here. I want you to ask questions from what I explained, because I told you this was a special class. I want you to ask questions. Concerning what I just said. Unless if there's no question, we'll proceed. I want you to ask questions. Because the concept of statistical test is what I've just given you. And the simplest to explain it is t-test. I'm telling you, it's even simpler than chi-square. But the reason you begin to, why did I start my training with chi-square? I have the reason because people have heard of chi-square more than any other thing, even though they don't know much about it. But most of this concept is better explained by quantitative variable, like this issue of t-test is better. So I want you to be sure that you have gotten the logic behind hypothesis test. It's some people that invented it. It's not as if maybe it came from heaven like that. It's some people that just use logic. Okay, let's use this. And that's how statistics develop. So I don't know if there's a question. So if you want to talk yourself, okay?
Dr. Dako,
yes, sir.
Yes, I'm trying to have a full understanding of what you mean by inherent variability.
Thank you. Okay. Inherent in the sense that even without your research in the population, how those attributes differ in the population generally, without even grouping. You know, this thing that we just did, I sampled 2 groups. But this is you that sampled them. It's you that divided into urban rural. Yeah. They are all population before. It's you that say you are comparing male and female. They are all together. Generally, how different? And I give an example. Like weight vary more than height in the population. Yes, and there's not much difference in height of people, but there's much difference in the weight of people. I don't know if you agree with that.
Yeah, I agree.
So naturally, weight is very more. The inherent variability in weight is more than the inherent variability in height. That's, I don't know if you have gotten it now.
Yeah, so even when you are
now, very more than anything, income in the population. While some people are making millions in a month, some people are not making thousands, using 10,000 in a month. Go on.
Okay. Now, what I want to know is that when you have a data with you, and all you are working with is the data that you have in your hands.
Yes.
Is statistics assuming that there must be existing population parameters somewhere that you are not aware of?
Yes. You know, you know why you are asking this question. All this lecture we have been giving because of your you may be in theater by that time. You were not, yes, you were not up to date. Yes, you were not up to date with all the lecture we have been giving, all those free ones. That is why you're asking the question. Because those are the things. When I started with a basic concepts of statistics. Basic concept.
Yeah.
And some of you'll be shocked that even many researchers, many people that they may not understand some basic. It's just like if you miss some things about your English in secondary school, even to hard to, if case not taken, you may not be able to correct it. Yes, I'm telling you, it's foundation. That's why you see the children that have gone all the nowadays that will put your look at some of the things you didn't know before. When you were even now, your children in kindergarten, they will tell you because of its foundation. So there are some basic, like when you in development work I discover that they use data. They don't even, none of them know the meaning of data. They just know the data the way the computer user uses, because to a computer user, data is information you load in. That's what some of them know. They don't even know the meaning of data. Even you see somebody that 1A-i advisor in development work that by reason they said they are doing this one. They don't know. There are some basic concepts. And that's why the white man think we are all stupid. If you said now if they do survey, they don't believe that African man can analyze, they just use them to collect the data and send it to them. They will now do some modeling and remove error. That's why they are the one telling us the infant mortality, maternal mortality in Nigeria. They tell us more something than ourselves. If you go to our ministry now, you won't get anything. They go to WHO, they will tell you something about Nigeria. So those are the things. So I talk about those basic subjects. So this question you ask now, where I talk about it is parameter and statistics. In fact, it started with population, concept of population and sample. As a researcher, you are interested in what is happening in the population, what is happening in the people, in the population. But because the population, most of them can be infinite, can be so large that you cannot go and carry out your observation for all the elements in the population. At the end of the day, you cannot even, apart from spending all the money, and still, you may not still capture all the whole population. Even when you say you want to attend to, like in Lagos where you are now, we're talking of you are close to me, even let's say adults, close to about around 10 million or more in Lagos, where you want to study adult alone. If you say, yes, I want to measure their weight, because I want to take everybody, you can spend so much money, you will not get everybody, because the day you come to my house, I travel out. So you will now meet somebody that just came from Canada that was not in Lagos before. Can you see now? Apart from that, the population is so large. So the researcher, what the researcher can do is to take sample. So sometimes they want to improve the representative, either representative or not representative. Sample is a subset. In as much as you cannot study the whole population, you study sample. That was called sampling error. That is, I don't know if you understand. You've heard of sampling error before. The sampling error is the difference in the measurement from the real one because you took sample. And you can reduce sampling error if you increase your sample size. The more you increase your sample size, your error will reduce. So when you take your sample, you now summarize it, like you calculate mean, median, mode, or percentage.
Whatever.
That thing you got is called statistic. Statistic without S. It's different from the subject statistics. It only carry S when they are more than one. Like when you say, our statistics are not encouraging. Infant mortality, maternal mortality, others, they are statistics because it's more than one. You are talking of plural form. But in singular form, it's statistic. That is when you summarize your sample, you do your sample, whatever you get, even sensitivity, specificity you do in the lab, is statistic because it's not all the population sample that's there. It's just some people. So anything you summarize with sample is called statistic. But the real thing exists, that's the question you have. The real thing exists in the population, only God knows, is the parameter. The real thing is parameter. Like now, infant mortality, maternal mortality ratio, infant mortality rate in the population is the real thing is parameter. But what we shall give out is statistic because it's just some people used to, it's not everybody eligible under that thing that are used to calculate it. So something exists somewhere in the population, and that's what you are interested in. So when you have summarized your sample now, the process of collecting data, summarizing your data, analyzing, arranging it, sorting it, and summarizing it is called descriptive statistics. Now you now want to know this statistics I've got it through descriptive statistics. Is it the same thing? Is it close to the population parameter? That is the realm of inferential statistics. And that's what we around all this our hypothesis testing using statistical tests. You want to be confident, 95% confident that yes, what I've gotten is close to what is in the population. That is inferential statistics. So this issue of purpose, they are all inferential statistics. But when you summarize all two, this is the mean. You know, you can do your mean, mode, and period even without doing any statistical test. That is descriptive statistics. But whereas when you begin to do all those things, it's inferential. Does it make more sense now, Dr. Balogun?
Yes, I completely understand you.
You
Thank
completely,
you.
yeah. So that is why the logic that when we first were explained this one, in my lecture on introduction to inferential statistics, we now thought that was where we talk about standard error. I don't know if you understand anything about sampling distribution, because that's where we talk. So when sampling distribution just means if you take many sample, many times concerning a particular thing, you take many sample, maybe 50, 100, as many times as you can take. There will be sampling variation. When you summarize it to get your statistic, you will not get the same thing. If you take sample of 200 now, you do something with it, you come with mean, mode, and median, and some percentages. If you take in the same population, take another sample, you will not, when you calculate your mean, mode, it may be close, it may not be the same. In some situations, they will be the same. Some, repetition, some, it will be less, some, it will be more. So if you do that now, 200 times, you have 200 value. So that one also, the pattern of occurrence, the distribution of those statistic value is called sampling distribution. I don't know if you understand. So if you take sample 150 times, you have summary 150 summary, and that 150 follow distribution also. So that one you can calculate, can add them together and calculate the average. It is believed when you calculate the average of a sampling distribution, it is believed that that average will be equal to the parameter in the population. I don't know if you got the logic. For example, now they do it in the lab. Now, when you try to measure something, you measure many times, now calculate the average, believing that when you calculate, you measure again, it can be more. You measure again, it can be less. You just measure many times, you now divide, believing that that average of it will be the real value. So when you in sampling distribution, the average of all the statistics will be equal to the parameter. If it is percentage you are looking for, proportion of something, if you do it many times, you get many value, calculate the average to be the right proportion in the population. If it's the mean you are calculating and a mean of something, you do it many times, you now calculate the means of the mean. It is believed that means of the mean is the mean in the population, that is the parameter. But because there are many of them now, it has mean you can calculate the standard deviation for your sampling distribution because it's already have mean now. You calculate average of all of them. You can also calculate how different each of them is from the mean you calculated. And that, when you calculate it, you get a standard deviation. That standard deviation of sampling distribution is called standard error. You get it now? So some people, they say standard error is population standard deviation. It's not true.
Thank you very much.
It's standard deviation of sampling distribution, but it is believed it is equal to the standard deviation in the population. You get the picture now? And that is why some people, it's like a proxy. That's why some people now call it standard error is the population standard deviation. It's not completely true like that. It's just a proxy. The standard error is standard deviation of sampling distribution because it is used to represent the standard deviation in the population. So you now see that is how the standard error came. But nobody does take sample many times. All this issue of taking sample many times came when the statistics are not developed. We were developing by that time. People go to casino. I don't know if you have Monte Carlo. That's of course, Monte Carlo is a French principality. They are under French. It's one small country like this one. What they do there is gambling, casino. That is where the statisticians go to collect data. Because in those days, people don't come to you and say, we are doing a study. It's strange. Nobody will even answer you. So what they were doing is gambling, the sort of gambling, naturally people go there. So the recording, they go and collect it there. That's what they were using to study statistics. So in that case, they can have many sampling distribution. They can have many sampling distribution. So now the intelligent people now got to know that you don't even need to take sample many times. That the sampling distribution usually depends on if you calculate the standard deviation divided by the sample size, square root of sample size. That is the standard error. The standard error is usually small when the sample size is high, and it's usually large when the sample size is very small. So what does that do is that you just divide your standard, just one sample you took, divide the standard deviation you got there with square root of cosine. That will be standard error. So that is where standard error is the measure of the inherent variability. Does it make sense now?
Yes.
Yes.
That is the variability in the population. So like just as I said, in the weight we have smaller standard error compared with height. Height we have smaller standard error compared with weight. Weight one with more because the variability in height is smaller. So that is just the logic behind it. So I think that one has answered the question you raised.
Yes, definitely.
Any other person, because you actually need it, because that is how this is realm of inferential statistics. That's how the logic, the thinking come from. So they look at the variation you observe between the observed and your expected, they now divide by the inherent variability. Because if something very naturally, you observing just between variation between two groups does not make a difference. Unless you divide it by the variability to really know, the variation I've seen in these two groups offset the inherent variability is so far higher than inherent variability. That shows that these two groups are different. That is why you now use the variability you observe in your study as the numerator, and the variability you observe in the inherent variability as the denominator, believing that if actually the variability you observe is really different, it will offset, it will be greater than inherent variability. If it's greater than, it will be greater than 1. Because when you divide something of the same, in fact, if the variability, inherent variability is more than the one you observe, the thing will be, when you divide it, it will be less than 1. That shows that there's not even different. But if it's going to be different, it should be greater than 1. If that way, because it's the numerator, it should be greater than the denominator. Not just greater than 1. It now reach a critical value. And that's, oh, no. This difference is statistically significant. That is why most statistics, as they increase, the probability that you have made type 1 error, that is the probability that the difference you are observing is due to chance, that actually is a chance occurrence, is reducing. That is why if it reduce, no, it's less than 0.05. No. The probability that is due to chance is very small. I don't think it's due to chance. It's a really different. Does it make sense now? It's only Mark Whitney U and the Wilkinson that differ. The smaller the value, also the smaller the probability. That's the only, and thank God we are treating it also in this study. Is the non-parametric counterpart of this t-test. They are the only statistic that as they decrease also the probability decreases. So as they decrease, the p-value decreases. It's not higher value now, it's lower value of it. I think we proceed. Bukola, any question? No question. Okay, let me continue sharing my distance. I just say you clarify.
Yes, sir. I'm actually trying to follow, but I'm distracted. Having a lot of distractions. Okay,
no problem. Let me just be following. Yes. Yeah. So what I just said now, if you look at it, if you now look at this formula now, the numerator we are seeing here, this is the observed difference. No, there are two groups. I'm just using two group example because they are the simplest to explain it. In two independent group. This is mean for group 1, mean for group 2. You remove it. That is the observed difference. This is the hypothesized difference. If the non-hypothesis were true in the population, this is the difference between the two. So if non-hypothesis is true, that difference will be 0. That is why it's no more, it's cancelled out of the equation. And this one you are seeing here is the standard error. But this formula look complex. It's a standard error for two groups. That is why I look at. Let me go to the next slide because I like. Look at this. Because this one is looking at one pair t-test and one sample t-test. You are just removing the population mean from the sample mean. It's only one sample you have. So the standard error is standard deviation S over square root of sample size.
Nice.
Is this same thing they put for 2, for group 1, group 2, that change to this? You just change of manipulation. That's your, so if you just look at, it's actually square root of S all over square root of standard deviation. Sorry, standard deviation without that square. You know, what you are seeing S square now is variance now. You are square this, but it's S all over square root of N. But they want to put all of them under square root so that you can add it together. It's like S1 all over square root of N1 plus S2 all over square root of N2. So that they can now put all of them together. Of course, the square, the N, both of them, they've already got a square root before. You want to extend the square root over to the S, you have to square it. If you have to put the S under square root, you square it. If you bring M out now, it becomes S all over square root of N. So it just, so it looks complex. It just is the standard error for the 2 groups of the different. The standard error of the different. That's what you are seeing. The 2 groups. So now look at it now, because we know that the hypothesized value of difference is 0. So you now come just for you to know the logic, because you know how to use the machine to run, but you know the logic behind it.
Sure.
Now, somebody want to ask a question?
Oh, go ahead.
So you now see we have different type. We are now have okay, type of the t-test. T-test is about comparing 2 means. It still remain like that, because the one sample t-test just mean that you have one sample. You are comparing. It has its own mean. You are comparing it with a mean in the population. You want to see? Oh, they have already done a study in the population. We have example like that. You're going to see we wrong. They already done, maybe it's in the population. That you have a quota mean in the population. Then your own, you have a sample. Not only that you know the mean of the sample, you also have the data set. So one sample t-test. Then we have the independent t-test. The independent samples, that is, there are 2 samples. The pair t-test mean that is one sample better. You take your measurement 2 times. It's the same one sample, but you measure before and after. You see, that's why they pair samples. So when they talk about samples as plural here now, they are not actually even talking about the group of subjects. It's the group of measurement. It's just like, look at it from the concept of the laboratory people. They say, I've taken a sample. It's not the person they take the blood sample from that is there in the lab. It's the blood sample. It's not the person. So when they say sample here, it's not the subject. It's the data you collected from the subject that is the sample. I don't know if you understand now. So that is the logic. So when they say pair samples, you took a sample, you collect an observation data from a group of people. The same group you collect again, you have 2 group of sample from the same group of people. The independent sample, you have sample from 2 separate groups. Yes. The one sample t-test is what, look at it. You have your sample, one sample, then this is mean, this is the population mean, and you over standard error of that sample you are having. So that's just the explanation. Yes. Let's use Dr. I don't know any other person. If you have downloaded, you see Ebola victim. One of the something. Let's run that one sample t-test and see the way it looks. Interpret it. That one sample. So, and see the way you run it. Okay, it's Dr. Who help us here? You see Ebola victim. Okay, look at this. It says the following is the age distribution of 20 victims of the disease during an outbreak in the country. The age was recorded in year. These are the, if you look at the 20. If the mean age of victim in a neighborhood country or neighboring country was 33 years, can we say that the mean age of affected victim is the same in the two countries? Can you see now? So when you say you are comparing one sample with a population, it may be the mean, it may be the same population where you take the sample from, or another population.
Another population.
It can be, yes. It's just that you have a sample you want to compare with a no mean in the population. So in this case now, is the mean of another population. This data set you see is a real one during Ebola. Is when I was doing training, one of the epidemiological team that these are the ages of people affected in Nigeria. So they were working although in Lagos, Abuja, they traveling around. So the lady now came to attend my training. You know, they gave them the data, they wanted to analyze the data. Now she has the data here and everything. So when the following day, when I was used to explain, they say discrimination. I said, is the name of these people are not there? He said, no, I did not say it's Ebola. That's why I removed Ebola. But in the in the name of this, I put Ebola, because as far as I'm concerned, they say they don't want, so that they will not know that these are the ages of the Nigerian. If they don't even know if the ages, do they know who are they are? Nobody knows they are. So it's these are the age distribution of people affected with Ebola in Nigeria right now. But that 50, the 33 I put, is mean I just put that value just to have a question out.
Yeah, sure.
So let me just stop sharing and let somebody share and go and read out some Ebola victim, and let's see the way we run it. I'm sure, Bukola, I'm sure you are not with your laptop. It's phone you are using.
No, sir, I'm with my phone. I'm at work. I'm not with my laptop.
Okay. It's like okay, Dr. Larry is here. Okay. Hey, Dr. Larry, help us share. Dr. Larry, see you help us share. Dr. Larry, are you hearing us? Dr. Larry, maybe it's not there. Just Professor Kidan, did you download this, sir? Prof, if you don't, Dr. Larry, Prof.
Yeah, somebody is distracting me here.
Okay,
yeah, I'm
yeah,
here with
no, I guess so. Okay,
I'm with you.
Hello? Maybe I should share my own.
Maybe you just share it.
Okay, because I actually want us to participate.
Okay, can I share, sir? Can I share?
Yes, you can share, sir. That's what I was calling. You can share, sir.